All right, so for section 313, we are going to expand what you already know about systems of equations. So hopefully you can think back, or even just from looking at this worksheet, you see these several different systems of equations. And a system of equations is just a way of saying more than one. So these sets of equations, this set of two in each of these examples, each of those is a system of equations, so more than one equation. In the past, we've learned that the solution to a system of equations, so if you're looking at the graph, is where those two graphs intersect. So the solution to a system is where the two graphs intersect. It's where their x and y coordinates are identical, and that would be the intersection. So if we're thinking of a visual here, and I have one equation that looks like this, and another equation that looks like that. So there's two different linear equations on the graph. Their solution would be that point right there. The x and y coordinates would be the same on each of those lines, and that is the solution to the system, which would be the xy coordinate that makes both equations true. Today we're going to add on to what you already know about that just by introducing one extra type of situation, which would be where, hold on, let me undo that last line I drew. So the situation would be, instead of two lines, what if I had a line and a parabola? So we're just going to be looking at two different types of equations now. So sometimes we'll look at a system of two lines, sometimes a parabola and a line, maybe two parabolas. But the idea, the overall concept of the solution being where those two intersect. We're going to talk about other types of solutions to systems as well. So let's just jump right into example. This first problem here, 345. So solve each system algebraically. So I know that we can use a graphing calculator, graph them, and look for their intersection, but we need to be able to show this algebraically. For each one, we're going to explain what the solution tells us about the graph. So I'll explain that as we go. Looking at this first system, I want to know where these two lines intersect. So as we've done, even on the last test we did, the first step here would be set these two equations equal to each other. So I have y equals this, but y also equals that. So if y equals both of those things, then I can just set them equal. So I'll start by doing that. Negative 3x plus 5 equals negative 3x minus 1. So at this point, I want to start solving by getting my x's all on the same side. So right now they're on separate sides. So the first thing I would do here is add 3x to both sides to continue solving. And you may have noticed right now that when I do that, negative 3x plus 3x is 0x. So what just happened here is I have 0x's left on this side, and 0x is left on the left as well. So what that leaves me is with 0x plus 5, or just 5, equals 0x minus 1. So my x's disappeared, and now I'm left with this statement, 5 equals negative 1. The problem is that that is not true. That is very false. 5 never equals negative 1. Not true, not equal. So what does this mean about our solution? There is no solution to this system. So there is no solution to this. So what does that mean about the graph of the system? What does that mean about the graph of the system, meaning both of these graphs at once? Well, if we think back, a system has its solution where the two graphs intersect, and if there's no solution, then there is no intersection to those two between those two graphs. So what that means is, since these are both lines and there's no intersection, the only possible way two lines never intersect is if our two lines are parallel. So these are parallel lines. So today we're going to be thinking about not just what the solution is to a system, but what the solution means. So this having no solution means these two graphs never intersect, and since they're both lines, they have to be parallel. Let me show you a quick graph of this system. All right, so here is a graph from my picture of my graphing calculator. These are the two lines. These graphs should make sense. A slope of negative 3x on both of them. One has a y-intercept of positive 5, that's the blue one up top. The other has a y-intercept of negative 1, that's the red one. So now we see visually that these are parallel. We also see that in the equation because they have the same slope. Lines with the same slope means they're parallel to each other, and they never intersect. So again, I know that we can look at this graph and tell that there is no solution to the system, but we want to move away from that and be able to show that or prove it with algebra, which is what we did here. All right, I'm going to get rid of that graph and we'll move on to example B. Okay, moving on to this example here in part B. I have both of these equations written in the form of y equals. So y equals this 1/2 x squared plus 1. Y also equals 2x minus 1. That means I can just set these two functions equal to each other since they both equal y. So it would be the equal values method. And I can set them equal. The only difference about this system from the ones that we've seen is that we no longer have two linear systems. I have one linear equation, 2x minus 1, and this one, this quadratic, and I can tell that from the x squared. So I'm going to start by setting those equal to each other, just like we did. So again, this is the equal values method that you've used in previous courses. So 1/2 x squared plus 1 equals 2x minus 1. And now my goal is to solve this. So I have a quadratic. My goal would be to get everything on one side of the equal sign. The tough thing here is that I'm dealing with a fraction, which is no problem because we have that fraction buster method. So I'm going to deal with that fraction first and multiply every single thing I see in this equation by 2. And that's going to get rid of that 1/2 out front, so I don't have to deal with fractions this whole time. So 2 over 2, that cancels, and I'm left with x squared plus 1 times 2, which is 2, equals 2x times 2, so 4x minus 1 times 2 minus 2. Okay, so now I'm going to get everything on the same side of the equal sign. So to do that, I need to subtract 4x from both sides. There's no x term on the left side. That's no problem. I also need to add 2 to both sides. Okay, so I'm adding 2, and so we end up with x squared on the left minus 4x, and then I added 2 to both sides, so that would be plus 4 equals 0. So I've gotten everything to one side of the equal sign, and now I have this quadratic that I'm going to try to factor. So I'm going to solve this, or factor this, using the diamond game. So put 4 here, negative 4 below, and I'm thinking of two numbers that multiply to positive 4 but add to negative 4. So that would be 2 and 2, and since they add to negative 4, both of those are negative 2's. So negative 2 times negative 2 is positive 4, but negative 2 plus negative 2 is negative 4. So that means my quadratic factors to x minus 2 times x minus 2 equals 0, which means x equals 2 and x equals 2. So this is only part of my solution because this is the x coordinate for where my two graphs intersect, and I still need to find the y value. So I would plug this x coordinate into one of these equations up here. I'm going to stick with that bottom linear equation because it's just a little easier to plug in 2 to that. So y would equal 2 times 2 minus 1, which is 3. So the solution, the end result here, my final solution is 2, 3. That is where these two graphs intersect. It is the solution to the system. So we can do this without the graph. We can take a quick look at the graph. So I'll pull that up. So here's a quick image of the graph. This is the parabola 1/2 x squared plus 1. Right here in blue, and then 2x minus 1, this line right here in red. So we can see visually from that solution, these two graphs intersect at just one point. This line sort of grazes the edge of the parabola right here at 2, 3, and that's the only point of intersection. So we can see it visually here, but again, understanding this algebraic process to do that is the goal here. So the solution is 2, 3, and what that means about the graph of the system, so like here we said that meant the graphs were the lines were parallel. In this example, it just means there is one intersection between these two graphs. So one intersection, and that takes place at 2, 3. Okay, let's take a look at these next two. Whoops, hold on here. All right, taking a look at part C. So I've got, again, a system of two equations, and one of them, the second one, is linear. The second one is not linear. In fact, it's not even in terms of y. So I can't use the equal values method because I don't have a y equals something and y equals something else. However, I do know that y squared equals x. So if x equals y squared, then we can use the substitution method because I have a solution for x here, and I have an x right here that I can make that substitution in for. So instead of y equals x minus 2, I can plug what x equals, which is y squared, in for x. So this y squared I will substitute in right there. So that's going to give me my first step here in the process of solving. So y equals, instead of x minus 2, I'm going to substitute y squared in for x minus 2. Okay, so now again I have y on one side, y squared on the other, and minus 2. This we can set up as a quadratic. So I see y squared, we should be thinking quadratic again. So instead of subtracting this y squared over to the left, which is where we're used to seeing it, I'm just going to subtract the y over so I can keep my y squared term positive. So I'm going to subtract y from both sides, and when I do, I will have this new equation, y squared minus y minus 2 equals 0. And here I just have another quadratic. So this is one that I would factor, or at least try to factor. So I will use my diamond game. So negative 2 up top, negative 2 in the bottom. Trying to think of two numbers that multiply to negative 2 and add to 1. The only two numbers that have a product of 2 are 2 and 1, 2 times 1. 2 would have to be negative and 1 is positive, and those would add to negative 1. Okay, so that would be negative 2 times 1 multiplies to negative 2. Negative 2 plus 1 is negative 1. So we have x, or y, minus 2 times y plus 1 equals 0. This gives me two solutions for y. Y equals positive 2, y equals negative 1. So it looks like because I have two y values in my solution, that this system will have two intersections. So I just need to find the x coordinate of those intersections. So up here I have x equals y squared. So all I need to do to determine x for each of these is to square the y value. So my first one here, if y equals 2, then x equals 2 squared, which is 4. So I have one intersection point at the coordinate 4 for x, 2 for y. That's the one I just got here. And then my second one, let's see what that x value would be. I just need to square negative 1. And negative 1 squared is positive 1. So this gives me an ordered pair of 1 comma negative 1. 1, negative 1. So we see this system has two solutions, which means it has two intersections. And then I'm going to show you a visual of this graph. Okay, so let's think about, we know this second equation, y equals x minus 2. That's a line with a slope of 1. A y-intercept of negative 2. This top one is not even in the form of y equals, it's y squared equals x. We have looked at this one before. It's kind of the exact opposite of y equals x squared, it's x equals y squared. So that's that sleeping parabola. And in order to enter that into the graphing calculator, I couldn't put x equals y squared, I actually had to solve for y, which meant I had to take the square root of both sides. So to do that, I had to take the square root of x, but when we do that, we have to account for both the positive and negative root of x, which is why this is not even a function. Remember that sleeping parabola. But when I enter these two separate functions into my y equals, then I can see the whole graph of y squared equals x. So let me show you a quick visual of that. All right, so here's the graph. This red piece right here, the top of the sleeping parabola, that's the positive square root of x. The pink one is the negative root. of x, and then I have the linear graph right here. So we can see these two solutions making sense when we look at it, 1, -1, and 4, 2, which again, I know that you can look at a graph and point to those intersections and explain them. However, the focus of this is to understand how to do that without looking at the graph and to back up our answers with the algebra. So now let's take a look at the last one. And here we have 4x minus 2y equals 10 and y equals 2x minus 5. So the strategy I'm going to use here, I cannot use the equal values method because that would mean I would need y equals for both of them. But I do have one of the equations in the form of y equals, so I can use the substitution method here. So if y equals 2x minus 5, then I can just replace this y with 2x minus 5. So that's how I'm going to set it up. So I'm going to rewrite this first equation here, 4x minus 2y, but instead of y, I'm going to write this whole thing, 2x minus 5 equals 10. So I'm finishing up by writing the rest of this whole equation and substituting 2x minus 5 in for y. Now I just have one variable x, and I can solve for x. The first step here, I've got a -2 out front of this parenthesis, so that means I need to distribute my -2 to both of those. So that'd be 4x, -2 times 2x, that would be minus 4x, and -2 times -5, that's going to be positive 10, equals 10. So 4x minus 4x, those are gone. I'm just left with 10 equals 10. So here I have a situation where my x term totally disappeared. I have no more x's. What happened? And I'm left with this statement, 10 equals 10. We saw this in example A, but I was left with a false statement. However, this statement, 10 equals 10, that is a true statement and will always be true. And what that means is that no matter what x value I plug in here for one of these, I'm going to get the same output as I would for the other equation. So basically it's saying it doesn't matter what x is, you're going to have the same y value if you use the same x value in each of these equations. So what does that mean visually? That means there are infinitely many solutions. So we'll write that and talk about what that means. There are infinitely many solutions. And that means, think about the graphs. If there's infinitely many solutions, meaning infinitely many intersection points between the graphs of each of these equations, that means it's the same exact graph, meaning same line. So they're written a little differently, but these two graphs are the same exact line. Let me show you a visual of that. Actually, I don't need to show you a visual. We can just piece it together because since it's 2x minus 5, I've got a y-intercept at -5 and a slope of 2, so it's going to look something like this. That's a very rough sketch of that. And if I solved for y from the top equation, it would give me the same exact graph. So we're looking at basically the same line, which means they intersect infinitely many times at every single point on each of the lines, which is why there are infinitely many solutions. So in these notes, this is where I'm going to stop. I've showed you 4 examples, and you have seen several different types of solution. So you're going to need to be able to explain, I guess, what no solution means about a system of equations. That would mean they never intersect. If you have a solution, either one solution or 2 solutions, that means that's how many times those 2 graphs intersect. So if you do come up with concrete solutions, those ordered pairs, that means there are intersections, or at least one. The last scenario is if you get a true statement when your x value or your variable disappears, then there are infinitely many. So these two here in this part A, the x's disappeared and we had a false statement. Here the x's disappeared and we had a true statement. So if you're left with a false statement, there simply is no solution. If you're left with a true statement, then there are infinitely many. So what I want you to do is try these 2 on your own. And then once you're finished with these 2, you're going to upload this to Schoology and we'll go over your solutions in class. But I do want you to do these 2 on your own before uploading. Let me just give you a couple of tips before you get started. So here on number 1, I do not have y equals and y equals. So in this first one, you're going to have to use that substitution method that we just did in part D. So I have y equals this, and then I can substitute that in for y right here. So you're going to have to make that substitution. Don't get too nervous about this fraction, because when you multiply 6 by everything in there, the fraction will reduce to an integer. So don't panic about that. Do your best and show me your solution. And on this one, we do have both of them in the form of y equals, so I can set them equal to each other. I'm going to write that first line out for you so I can set these equal to each other. 2x plus 4 equals x plus 1 squared plus 3. I'm doing this because I want to point out that x squared plus 1, or x plus 1 squared, is not x squared plus 1 squared. You need to distribute this. This is, do the work to get what this would equal when you actually distribute x plus 1 times x plus 1. So make sure you are doing that correctly. So your next line would be this. So do this distribution and simplify both sides. What you'll end up with is a quadratic that you should be able to solve very easily, actually. So good luck on these, and when you're finished, upload them to Schoology, and I'll see you soon.